Think about these two phrases, river bank and financial bank. The word bank is the same in both the phrases, but the meaning is completely different. Before 2018, most embedding models treated them exactly the same way. They assigned the same embedding vector to the word bank, no matter the context. In this video, I will show you how embeddings evolved from being static and limited to dynamic and context-aware. And more importantly, why this change is so critical for everything we do in AI today. Let's go! By now, you have seen tokenization, where our text becomes tokens and tokens get converted into numbers. Say you type, "Hello world, how are you doing today?" The tokenizer breaks this sentence into smaller pieces. You get tokens like hello, world, how, and so on. Now, each of these tokens is assigned a number or an ID. For instance, hello might become 15496 and world might become 3029. So, what the model actually receives is a sequence of numbers like 15496, 3029, etc. These numbers are not random, they are determined during the tokenizer training process using algorithms like BP, which we discussed earlier. But these numbers are just IDs. They are just positions in a vocabulary. They do not carry any meaning. If I tell you that hello is 15496 and hi is 22000, you cannot tell that these two words are similar just by looking at the numbers. So, this is the gap in tokenization. Token IDs are meaningless numbers. They do not capture the actual meaning of words. And this is exactly where embeddings come in. An embedding takes a token ID and maps it to a dense vector in a high dimensional space. A vector in this context is simply an ordered list of real numbers. For example, 0.52 minus 0.23, 0.81, 0.15, etc. These values are not arbitrary. They are learned during training and represent different latent features of the token. For instance, consider the token AND, which might have a token ID of 8. Its embedding would be a learned vector with values like 0.0523 minus 0.0208 and so on. Each dimension of the vector captures some aspect of the word's behavior in language. For example, certain dimensions may encode syntactic properties such as whether a word functions as a noun or a verb, while others may capture semantic properties such as sentiment, domain, or usage patterns. Now, an important property of embeddings is that they preserve the semantic similarity. Tokens that appear in similar contexts tend to have similar vector representations. So, the embeddings for dog and cat will be close to each other in this vector space, while dog and car will be much further apart. Another powerful property is that these vectors support linear operations. For example, if you take the embedding for king, subtract the embedding for man, and add the embedding for woman, you obtain a vector that is very close to the embedding for queen. King minus man plus woman equivalent to queen. This happens because embeddings encode relational structure in the vector space. This was a major breakthrough in representing language numerically. However, these embeddings are still static. They assign a single vector to each word, regardless of context. And that limitation leads us to the next step in their evolution. Let me take you back to 2013. That's when Google introduced a technique called word-to-vec. Word-to-vec is a shallow neural network that learns to represent words as dense vectors, typically in a 300-dimensional space. Instead of assigning random numbers, it learns these vectors based on how words appear in local context windows. In simple terms, words that appear in similar context end up with similar embedding. Word-to-vec primarily uses two training architectures, CBOW or continuous bag of words, which predicts a word based on its surrounding context, and skipgram, which predicts surrounding words given a target word. Then came another important technique from Stanford University called GLOVE, or Global Vectors for Word Representation. Unlike word-to-vec, which focuses on local context, GLOVE captures the global statistical information. It analyzes how frequently words co-occur across an entire corpus and uses this co-occurrence statistics to learn embeddings. These allows GLOVE to capture broader semantic relationships in language. Both word-to-vec and GLOVE were powerful, but they had a fundamental limitation. In both models, each word is assigned a single fixed vector. Why is this a problem? Because meaning in language is context dependent. The same word can represent completely different concepts depending on how it is used. These embeddings are static. They are pre-trained once and then frozen. They do not adapt based on the context. If you want me to go deeper into what to wake or glove, feel free to drop a comment. Then, around 2018, everything changed. Models like ELMo, BERT, and later GPT introduced a new idea that is called contextual embeddings. These embeddings are dynamic. The representation of a word now depends on the entire sentence. This shift from static to contextual embeddings is what made modern language models possible. Now, we will talk about the contextual embedding models. ELMo is the first one, stands for Embeddings from Language Models. It was invented in 2018 by researchers at the Allen Institute for AI. It was one of the first models to generate contextual embeddings. Unlike what to fake or glove, ELMo does not assign a single fixed vector to a word. Instead, it generates embeddings based on the entire sentence. Technically, ELMo uses bidirectional LSTMs. This means it reads the sentence from left to right and from right to left and combines both directions to understand the context. But ELMo still had limitations. It was computationally expensive, and LSTM struggled to scale efficiently for very large datasets. Then BERT arrived. It stands for Bidirectional Encoder Representations from Transformers. It is a groundbreaking Google-developed AI model released in 2018. This model moved away from LSTMs and uses the encoder part of the transformer architecture. One key idea in BERT is bidirectional context. Unlike previous models, BERT looks at both the left and right context of a word simultaneously, and which leads to better language understanding. BERT is trained using two main methods: masked language model or MLM and next sentence prediction or NSP. Pre-trained BERT models can be easily fine-tuned using Hugging Face transformers for specific tasks like classification, sentiment analysis, or question answering. Then came GPT, Generative Pre-trained Transformer by OpenAI in December 2022. Unlike BERT, GPT is designed for text generation. It uses a unidirectional transformer, which means it reads the text from left to right, and at each step, it predicts the next word based on the previous words. This makes it extremely powerful for tasks like text generation, conversation, code generation, and etc. Models like ChatGPT was built on top of this idea. So now, you have seen how embeddings evolved from static representations like what to wake and glove to contextual models like ELMo, BERT, and GPT. This shift is what made the modern AI systems possible. But here is the next question. How does a model actually understand the sequence of words? How does it process the language step by step? Before transformers, models like RNNs and LSTMs were used to solve this problem. In the next video, we will break down how these models work and why they were such an important step in the evolution of AI. If this helped you understand things better, don't forget to like, subscribe, and hit the bell icon. And if you have any questions or want me to go deeper into any topic, drop a comment below. I will see you in the next video. Till then, goodbye and happy learning.